Tonight, we're hunting for the most powerful thing in the entire universe. You might think the answer is obvious. Maybe it's an exploding star, releasing more energy in seconds than our sun will produce in its lifetime. Maybe it's a black hole, warping space-time so severely that nothing can escape. Maybe it's something even more extreme, something that briefly outshines every star in the cosmos. But the real answer might not be what you expect. The universe's most powerful force doesn't announce itself with light or sound. It operates on a scale that makes even the most violent explosions seem small. And it's been determining the fate of the cosmos since the beginning. By the end of tonight, you're going to discover what it is and why it's more powerful than anything else in the universe. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand what makes something powerful in the universe, we first need to establish what we mean by power. In physics, power is the rate at which energy is transferred or converted. It's not just about how much energy something contains, it's about how quickly that energy is released or how dramatically it affects its surroundings. Think about it this way: a baseball has a certain amount of energy stored in it, enough for a strong throw. Now, imagine for a moment that you could take all of that energy and choose how fast to release it. If you spread it out over a long period, like gently rolling the ball across the ground, nothing dramatic happens. The ball moves a short distance, barely pushes anything. The energy is the same, but the power, how fast it's released, is low. But if you release all of that energy in an instant, like throwing the ball as hard as possible, all that energy comes out at once, creating a huge effect. The ball soars through the air, smashes into the glove, or hits a bat with surprising force. Same energy, completely different impact, because now the power is high. This is exactly the same principle behind explosions, engines, and even extreme events in the universe. Energy may be the same, but power can make all the difference. This distinction becomes even more dramatic when we scale up to cosmic phenomena. A star like our Sun is incredibly energetic, fusing 620 million tons of hydrogen into helium every single second. Each second, the Sun converts about 4 million tons of matter directly into pure energy, according to Einstein's equation E equals mc squared. The Sun's total power output is about 384 septillion watts. That's a 3 followed by 26 zeros. Every second, the Sun produces more energy than humanity has used in our entire history. But here's the thing: the Sun will shine for about 10 billion years total. It's spreading its enormous energy output across an incomprehensibly long time span. The Sun is like a savings account, with a massive balance that pays out a steady, reliable amount every day for billions of years. Now compare that to a supernova, the explosive death of a massive star. A supernova releases as much energy in a few weeks as our Sun will produce in its entire 10 billion year lifetime. That's not a savings account, that's winning the lottery and spending it all in a single weekend. The power output of a supernova at its peak can reach 10 billion trillion watts. That's 10 to the 37 watts, about 25 trillion times more powerful than the Sun. For those few weeks, a single dying star can outshine an entire galaxy containing hundreds of billions of normal stars. That's power. That's the concentration of cosmic fury we're searching for. But power in the universe isn't just about brightness or energy release. There are other ways to measure cosmic might. Some objects don't shine brightly, but they warp the fabric of space-time so severely that they trap light itself. Black holes represent power through gravitational dominance, bending space and time into configurations that seem to violate common sense. Near the event horizon of a black hole, Time itself slows down relative to the outside universe. If you could somehow hover just above the event horizon of a supermassive black hole and stay there for 1 hour, decades or even centuries might pass in the outside universe, depending on how close you are. That's a form of power, the power to manipulate the flow of time itself. Other objects generate magnetic fields so intense they alter the quantum vacuum and change the fundamental behavior of matter. Some phenomena create ripples in spacetime that propagate across the universe at the speed of light, carrying information about cataclysmic collisions that occurred billions of years ago. And some forces operate so subtly that we didn't even know they existed until recently, yet they control the ultimate fate of everything that exists. So, as we journey through the cosmos tonight, we're going to evaluate power in multiple ways. Raw energy output, measured in watts or joules per second. Total energy released, measured in joules. Gravitational influence, measured by how severely space-time is warped. Magnetic field strength, measured in Gauss or Tesla. And cosmic significance, measured by how much influence a phenomenon has on the structure and fate of the universe itself. By the end, you'll see that the answer to what's the most powerful thing in the universe depends on which metric matters most. But one phenomenon will emerge as the clear winner when we consider total cosmic influence. Let's begin our search with the most visually spectacular displays of power in the cosmos, the deaths of massive stars. When a star at least 8 times the mass of our Sun reaches the end of its life, it goes out in the most spectacular way possible. But to understand why this happens, we need to understand what a star really is. A star is a battleground between two fundamental forces. Gravity is constantly trying to crush the star into the smallest possible volume. Every atom in the star is pulling on every other atom, trying to collapse the entire structure into a point. But nuclear fusion in the core produces outward pressure that counteracts gravity's inward pull. As long as fusion continues, the star remains in balance. This balance is called hydrostatic equilibrium, and it's the state our Sun has maintained for the past 4.5 billion years. But fusion requires fuel, and eventually that fuel runs out. For a massive star, the end is a multi-stage process that plays out over millions of years. First, the star burns hydrogen in its core, fusing it into helium. This phase lasts for millions of years, depending on the star's mass. More massive stars burn through their fuel much faster because they need higher core temperatures and pressures to support their greater weight. A star 10 times the mass of the Sun might only live for 20 million years, compared to the Sun's 10 billion year lifespan. When the hydrogen in the core is exhausted, the core begins to contract under its own weight. This contraction heats up the core until it reaches 100 million degrees, hot enough to begin fusing helium into carbon and oxygen. Meanwhile, a shell of hydrogen around the core continues to fuse, and the outer layers of the star expand dramatically. The star becomes a red giant, or, for very massive stars, a red supergiant. When the helium runs out, the core contracts again, heating up until carbon fusion can begin. Carbon fuses into neon, magnesium, and other elements. Then neon burns. Then oxygen. Each successive stage happens faster and at higher temperatures. Carbon burning might last for 1,000 years. Neon burning lasts about a year. Oxygen burning lasts for months. Finally, the core begins fusing silicon into iron. Silicon burning lasts for just a few days, and then the star faces a fundamental problem. Iron is the most stable nucleus in the universe. Fusing iron doesn't release energy. It requires energy. You can't get power out of iron fusion. You have to put power in. The core, now composed of pure iron, can no longer support itself. For For the first time in the star's life, there's no fusion generating outward pressure. Gravity wins. What happens next occurs so fast that if you blinked, you'd miss it. In less than 1 second, the iron core collapses. Material that was once spread across a region the size of Earth, with a mass perhaps 1.5 times that of our Sun, gets compressed into a sphere just 12 miles across. The density becomes so extreme that electrons are forced into protons, creating neutrons and releasing neutrinos. The core becomes a neutron star, one of the densest forms of matter in the universe. A teaspoon of neutron star material would weigh about 4 billion tons on Earth, about the same as every car on the planet combined. The collapse happens at about 1/4 the speed of light. That's 46,000 miles per second. The outer layers of the star, suddenly deprived of the support they've relied on for millions of years, begin to fall inward. They're accelerating in the immense gravitational field of the collapsing core, picking up speed as they plummet toward the center. When this infalling material hits the incompressibly dense neutron star core, it rebounds. The core is so dense that it's essentially a giant atomic nucleus, the size of a city. The infalling matter bounces off it like a ball bouncing off concrete. This rebound creates a shockwave that propagates outward through the star. The shockwave alone would be enough to blow the star apart, but there's another source of energy at play. During the core collapse, an enormous number of neutrinos are released. Neutrinos are ghostly particles that rarely interact with matter. Under normal circumstances, neutrinos pass through the entire Earth as if it weren't there. About 100 trillion neutrinos from the Sun pass through your body every second, and you never notice because they almost never interact with your atoms. But in the extreme conditions of a supernova core, the neutrino flux is so intense that even though each individual neutrino has only a tiny chance of interacting with matter, the sheer number of them means they deposit tremendous energy into the surrounding material. About 99% of the supernova's total energy output is carried away by neutrinos. Only 1% goes into the visible explosion, the light and kinetic energy of the blast. But that 1% is still enough to outshine a galaxy. The shockwave, boosted by neutrino energy, blasts through the outer layers of the star at speeds of up to 30,000 miles per second. That's about 15% the speed of light. The temperature in the shockwave reaches billions of degrees. At these temperatures, nuclear reactions occur that create elements heavier than iron, gold, platinum, uranium, thorium, and all the other elements that can't be created by normal stellar fusion are synthesized in the intense environment of the supernova. These newly forged atoms are scattered across space, seeding future generations of stars and planets. Every atom of gold in your jewelry was created in the heart of an exploding star. Every atom of uranium in nuclear reactors came from supernovae. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in stars and distributed by supernovae. We are, quite literally, made of star stuff. The visible light from a supernova can be detected from billions of light years away. For a few weeks, a single dying star can output as much light as an entire galaxy of hundreds of billions of stars. The total energy released in the explosion is approximately 1 or 2 times 10 to the 46 joules. To put that in perspective, that's more energy than our Sun will produce in its entire 10 billion year lifetime, released in a matter of weeks. The most famous supernova in recorded history occurred in 1054 AD. Chinese and Arab astronomers documented a guest star that appeared in the constellation Taurus and was visible in daylight for 23 days. At night, it was bright enough to read by. That supernova left behind the Crab Nebula, an expanding cloud of gas and debris that we can still observe today. In 1987, a supernova occurred in the Large Magellanic Cloud, a small galaxy orbiting the Milky Way, just 160,000 light-years away. Supernova 1987A was the closest supernova observed since the invention of the telescope. Astronomers detected not just the light from the explosion, but also the neutrinos. About 24 neutrinos from the supernova were detected by neutrino observatories on Earth. Out of the 10 to the 58 neutrinos released by the explosion, only about 24 made it through our detectors. But those 24 neutrinos confirmed our theories about how supernovae work and proved that neutrinos carry away most of the energy. Supernovae occur roughly once per century in a typical galaxy like the Milky Way. We're actually overdue for one in our galaxy. The last confirmed Milky Way supernova was in 1604, observed by Johannes Kepler. When the next one occurs, assuming it's reasonably close, maybe a few thousand light-years away, it will be an extraordinary sight. It might briefly become the brightest star in the sky, visible even in broad daylight. But as spectacular as regular supernovae are, they're not the most powerful stellar explosions. Some stars die even more violently. These events are called hypernovae, and they're 10 to 100 times more energetic than regular supernovae. Hypernovae occur when extremely massive stars, perhaps 50 to 100 times the mass of the Sun, collapse to form black holes instead of neutron stars. The physics of a hypernova is similar to a regular supernova, but everything is amplified. The core is more massive, the collapse is more violent, and the energy release is far greater. But there's an additional factor that makes hypernovae truly extraordinary: rotation. Most stars rotate to some degree. As the core of a massive star collapses, conservation of angular momentum causes it to spin faster and faster. Just like a figure skater pulling in their arms during a spin. If the core is rotating fast enough, the centrifugal force can prevent it from collapsing into a perfect sphere. Instead, it flattens into a rapidly spinning disk. The supernova explosion, instead of expanding equally in all directions, gets focused into two jets that blast out from the poles of the spinning core. These jets are narrow, perhaps just a few degrees wide, but they're incredibly powerful. They contain matter moving at 99.9% the speed of light or faster. At these velocities, relativistic effects come into play. The mass of the particles increases, time slows down for them, and the energy they carry becomes almost unimaginable. When one of these jets happens to be pointed at Earth, we detect something even more spectacular than a regular supernova. We detect a gamma-ray burst, the most powerful explosions in the universe since the Big Bang. Gamma-ray bursts are the most energetic explosions in the universe since the Big Bang itself, and their discovery is one of the most fascinating stories in modern astronomy. They were first discovered by accident in the late 1960 seconds by military satellites designed to detect gamma rays from secret nuclear weapons tests. During the Cold War, the United States and the Soviet Union had signed the Partial Nuclear Test Ban Treaty, which prohibited nuclear weapons tests in the atmosphere, in outer space, and underwater. To verify that the Soviets weren't cheating, the US launched a series of satellites called Vela, designed to detect the gamma rays that would be produced by a nuclear explosion. The Vela satellites worked perfectly. They could detect nuclear tests from anywhere on Earth or in near-Earth space. But they also detected something completely unexpected: bursts of gamma rays coming from deep space. These bursts were clearly not coming from Earth or from human-made weapons. They came from random directions in the sky. They varied in duration from a fraction of a second to several minutes, and they were incredibly energetic. The discovery was kept classified for several years because the Vela satellites were part of a classified military program. Finally, in 1973, the data was declassified and published in a scientific paper. Astronomers were baffled. What could produce such powerful bursts of gamma rays? The problem was that gamma-ray detectors couldn't determine the exact position of the bursts with high precision. Without precise positions, optical telescopes couldn't follow up to see what was at the location of the burst. For more than 20 years, gamma-ray bursts remained one of the greatest mysteries in astronomy. Hundreds of theories were proposed. Maybe they were from neutron stars in our galaxy experiencing starquakes. Maybe they were from comets falling into neutron stars. Maybe they were from colliding asteroids in the solar system, somehow producing gamma rays. Maybe they were from evaporating black holes. Maybe they were from some exotic form of matter we hadn't discovered yet. The debate raged because without knowing how far away the bursts were, it was impossible to calculate how much energy they were actually releasing. If the bursts were relatively nearby, within our galaxy, they might be relatively low-energy events. If they were coming from distant galaxies, they had to be extraordinarily powerful to be detectable from such vast distances. The breakthrough came in 1997 when a satellite called BEPO-SAX managed to detect a gamma-ray burst and immediately relay its position to ground-based telescopes with enough precision that they could point at the right spot in the sky. For the first time, astronomers observed the afterglow of a gamma-ray burst in visible light. They measured the redshift of the light, which told them how far away it was. The answer shocked everyone. The burst had originated from a galaxy more than 6 billion light-years away. 6 billion light-years. The light from that explosion had been traveling through space for 6 billion years before reaching Earth. The implications were staggering. If a gamma-ray burst could be detected from 6 billion light-years away, it must be releasing an absolutely incomprehensible amount of energy. We now know that there are two main types of gamma-ray bursts. Short-duration bursts, lasting less than 2 seconds, are produced when two neutron stars collide and merge, or when a neutron star merges with a black hole. Long-duration bursts, lasting anywhere from 2 seconds to several minutes, are produced by hypernovae, the deaths of the universe's most massive stars. Let's focus on the long-duration bursts, because these are the true cosmic monsters. When a hypernova creates a gamma-ray burst, it releases more energy in 10 seconds than our Sun will produce in its entire 10 billion-year lifetime. Let me say that again because it's almost impossible to comprehend. In 10 seconds, a gamma-ray burst releases more energy than the Sun will produce in 10 billion years. But unlike a regular supernova, which radiates energy in all directions more or less equally, a gamma-ray burst focuses much of its energy into two narrow jets shooting out from the poles of the collapsing star. These jets contain matter moving at 99.99% of the speed of light or faster. Some jets have been measured moving at 99.9995% of the speed of light. At these velocities, relativistic effects become extreme. According to Einstein's theory of special relativity, as an object approaches the speed of light, its mass effectively increases from the perspective of an outside observer. Time slows down for the object. Lengths contract in the direction of motion, and the energy required to accelerate the object further grows without limit. At 99.9995% of the speed of light, the relativistic factor, called gamma, is about 300. This means that from our perspective, 1 second in the jet's reference frame corresponds to 300 seconds in ours. The jet's effective mass is 300 times its rest mass, and the kinetic energy of the particles in the jet is roughly 300 times what it would be in classical physics. The jets plow through the outer layers of the exploding star, punching through and emerging into interstellar space. As they propagate outward, they collide with gas and dust in the surrounding environment, creating shock waves that heat the material to billions of degrees. This heated material produces the gamma rays we detect. The gamma rays are the most energetic form of light in the electromagnetic spectrum. They have wavelengths shorter than the diameter of an atom and energies millions of times greater than visible light photons. A typical long-duration gamma-ray burst releases approximately 10 to the 51 joules of energy. That's 1 followed by 51 zeros. That's 100,000 times more energy than a regular supernova. To put this in perspective, let's compare it to more familiar explosions. The atomic bomb dropped on Hiroshima released about 63 trillion joules of energy. A gamma-ray burst releases about 10 to the 38 times more energy than that. If you took every nuclear weapon that exists on Earth, about 13,000 warheads, and detonated them all simultaneously, you'd release about 10 to the 18 joules. A gamma-ray burst releases 10 to the 33 times more energy than every nuclear weapon on Earth combined. The most powerful gamma-ray burst ever detected occurred on the 9th of October 2022. Designated GRB 221009A, it was detected by multiple satellites and was so bright that it temporarily blinded some gamma-ray detectors. The burst came from a galaxy about 2 billion light-years away in the constellation Sagitta. Despite the enormous distance, it was the brightest gamma-ray burst ever recorded. Astronomers calculated that it released energy equivalent to converting several solar masses directly into pure radiation. The burst disrupted Earth's ionosphere, the layer of charged particles in the upper atmosphere. This is remarkable because the burst occurred 2 billion light-years away. The gamma rays had been traveling through space for 2 billion years, spreading out and weakening as they went, and they were still powerful enough to affect our planet's atmosphere. If a gamma-ray burst like GRB 221009A occurred within a few thousand light-years of Earth, and one of the jets happened to be pointed directly at us, the consequences would be catastrophic. The burst of gamma rays would hit Earth's atmosphere and create a shower of secondary particles. These particles would strip away the ozone layer within seconds. Without the ozone layer, to protect us from ultraviolet radiation from the sun, the surface of Earth would be bathed in harmful UV light. Marine phytoplankton, which form the base of the ocean food chain and produce about half of Earth's oxygen, would die off. Plants on land would be severely damaged. The entire biosphere would be disrupted. Mass extinction would follow. Some scientists have proposed that a gamma-ray burst might have been responsible for the Ordovician extinction event 440 million years ago. The Ordovician extinction was the second largest mass extinction in Earth's history, wiping out about 85% of marine species. The extinction seemed to occur in 2 pulses and appeared to be caused by a sudden increase in harmful radiation. There's no definitive proof that a gamma-ray burst caused it, but the timeline and the nature of the extinction are consistent with a gamma-ray burst striking Earth. Geological evidence suggests that Earth's ozone layer was severely depleted during this period, which would be exactly what we'd expect from a gamma-ray burst. Fortunately, gamma-ray bursts are rare. They occur perhaps once every few 100,000 years in a typical galaxy, and the jets are narrow, only a few degrees wide. So even if a hypernova occurred relatively nearby, say within 10,000 light-years, we'd only be in danger if we happened to be in the line of fire. The odds of a gamma-ray burst threatening Earth in any given million-year period are estimated to be quite small, perhaps 1 in a few 100,000. But the fact that it's possible at all is sobering. The universe contains phenomena powerful enough to cause mass extinctions across interstellar distances. And yet, as powerful as gamma-ray bursts are, they're transient events. They last for seconds or minutes, then fade away. The hypernova that produces the burst might shine brightly for weeks or months afterward as a supernova, but the gamma-ray burst itself is over quickly. There are objects in the universe that sustain enormous power output over much longer timescales. Objects that shine with the luminosity of trillions of suns, not for seconds, but for millions of years. These objects are called quasars, and they represent power on a completely different scale. The name quasar is short for quasi-stellar radio source, a name that reflects the confusion astronomers felt when they first discovered these objects. When they were first discovered in the 1960 seconds, they looked like stars in optical telescopes, but they emitted powerful radio waves, which stars don't typically do. Even more puzzling was the fact that their light was dramatically redshifted, indicating they were billions of light-years away. But if they were that far away and still appeared as bright as stars in our telescopes, they had to be producing an absolutely staggering amount of light. The first quasar was identified in 1963 by astronomer Martin Schmidt. He was studying an object called 3C273, which appeared to be a dim blue star with unusual radio emissions. When he analyzed the spectrum of its light, he found emission lines that didn't initially make sense. The patterns were wrong for any known element. Then he realized what he was seeing. The emission lines were from hydrogen, but they were redshifted so dramatically that they'd been displaced far from their normal positions in the spectrum. When he calculated the redshift, he found that 3C273 was receding from us at about 16% the speed of light. According to Hubble's law, which relates recession velocity to distance, this meant 3C273 was about 2.5 billion light-years away. But 3C273 appeared as bright as a 13th magnitude star in our sky. For it to appear that bright from that distance, it had to be intrinsically luminous beyond anything astronomers had ever encountered. Schmidt calculated that 3C273 was about 2 trillion times more luminous than the Sun. 2 trillion. That's more luminous than our entire galaxy, which contains hundreds of billions of stars, one object, outshining all of them combined. The discovery revolutionized astronomy. Over the following years, thousands more quasars were discovered. The most luminous quasars shine with the brightness of more than 100 trillion suns. Let that sink in for a moment. 100 trillion suns. Our entire Milky Way galaxy contains somewhere between 200 and 400 billion stars. A single quasar outshines several hundred galaxies like ours. What could possibly generate that much power? The answer, astronomers eventually realized, is a supermassive black hole actively feeding on matter. At the center of most large galaxies, including our own, there's a supermassive black hole containing anywhere from millions to billions of times the mass of our Sun. In the Milky Way, our central black hole, Sagittarius A star, has a mass of about 4.3 million suns. It's relatively quiet right now, occasionally snacking on stray gas clouds but not actively feeding. But in the early universe, and in some galaxies today, these supermassive black holes are surrounded by thick disks of gas and dust spiraling inward. This structure is called an accretion disk. As material in the accretion disk spirals toward the black hole, it accelerates to a significant fraction of the speed of light. Particles in the inner accretion disk, just outside the event horizon, can be moving at 10 to 30% of the speed of light. At these speeds, friction within the disk becomes intense. Particles collide with each other, transferring kinetic energy into heat. The temperature in the inner accretion disk can reach millions or even tens of millions of degrees. At these temperatures, the disk doesn't just glow, it blazes with radiation across the entire electromagnetic spectrum, from radio waves to visible light to X-rays and gamma rays. The inner region of the accretion disk, just outside the event horizon of the black hole, becomes one of the hottest and most energetic places in the universe. But here's the remarkable thing. The black hole itself isn't producing the energy. In fact, Anything that crosses the event horizon is lost forever. Its energy trapped behind a one-way barrier in space-time. No information, no energy, no matter can escape from inside the event horizon. That's the definition of a black hole. The power of a quasar comes from matter that hasn't yet fallen in, matter that's in the process of being devoured. As particles in the accretion disk collide and interact, they convert their orbital kinetic energy and gravitational potential energy into heat and light. This process is extraordinarily efficient. Nuclear fusion, the process that powers stars, converts about 0.7% of matter's rest mass into energy. That's the basis of E equals mc squared as it applies to stellar fusion. When hydrogen fuses into helium, about 0.7% of the original mass is converted into energy. Matter falling into a black hole can convert up to 10% of its mass into energy before crossing the event horizon, depending on the black hole's spin and the geometry of the accretion disk. For a rapidly spinning black hole with an optimal accretion disk, the efficiency can reach as high as 42%. That's 60 times more efficient than nuclear fusion. Think about what this means. If you drop 1 kilogram of matter into a supermassive black hole with an optimal accretion disk, you can extract up to 420 grams worth of pure energy, according to E equals mc squared. That's about 3.8 times 10 to the 16 joules from 1 kilogram of matter. For comparison, burning 1 kilogram of gasoline releases about 46 million joules. Dropping matter into a black hole is about 800 million times more energy efficient than burning gasoline. A quasar can convert the mass equivalent of 10 suns per year into pure radiant energy. 10 entire suns, annihilated and transformed into light every single year. And this can continue for millions of years, as long as there's fuel to feed the black hole. The radiation from a quasar is so intense that it can affect the entire host galaxy. The energy output creates powerful winds that blow gas and dust out of the galaxy's central regions, shutting down star formation. This process is called feedback, and it's one of the key mechanisms regulating galaxy growth. Without feedback from the central black hole, galaxies would convert too much of their gas into stars too quickly, and they'd look very different from the galaxies we observe. In this way, the supermassive black hole at the center of a galaxy acts as a thermostat. If the black hole becomes too active, it blows away the gas needed to form new stars and to feed itself. This causes its own activity to decline, allowing gas to settle back into the galaxy. Eventually, enough gas accumulates near the center, the black hole flares up again, and the cycle repeats. When we observe distant quasars, we're seeing this process in action. We're looking back billions of years to an era when supermassive black holes were actively growing, voraciously consuming the gas-rich environments of the early universe. The most distant quasars we've discovered are so far away that we're seeing them as they existed when the universe was less than 1 billion years old. These ancient quasars tell us that supermassive black holes formed very quickly in the early universe. Some of these early black holes already contained billions of solar masses when the universe was just a few 100 million years old. How they grew so large so quickly is still a matter of active research and debate. Today, most supermassive black holes have exhausted their fuel supplies. They sit quietly at the centers of galaxies, occasionally flaring up when a star wanders too close or a cloud of gas falls in, but mostly dormant. Our own Sagittarius A star is in this dormant state. It's there, lurking at the center of the Milky Way, but it's not producing anything like the energy output of a quasar. In about 4 billion years, when the Milky Way collides with the Andromeda galaxy, the gravitational disruption might funnel large amounts of gas toward both central black holes. If that happens, both Sagittarius A star and Andromeda's central black hole might briefly become quasars again, shining with tremendous power for a few million years before settling back into dormancy. But in their prime, quasars were the brightest beacons in the cosmos, visible across the entire observable universe. The light from the most distant quasars has been traveling toward us for more than 13 billion years, crossing most of the observable universe. And we can still detect them, still measure their spectra, still study their properties. That's a testament to the incredible power they generate. Quasars represent a specific phase of a broader category of objects called active galactic nuclei. Not all active galactic nuclei are bright enough to be classified as quasars, but they all share the same basic mechanism: a supermassive black hole actively accreting matter. And some of them produce something even more spectacular than the intense radiation of the accretion disk. They produce jets that extend for millions of light-years across intergalactic space. These jets from active galactic nuclei are some of the most extraordinary structures in the universe. Unlike the jets from gamma-ray bursts, which last for seconds or minutes, the jets from active galactic nuclei are sustained for millions of years. Their channels of plasma and high-energy particles, accelerated to nearly the speed of light by powerful magnetic fields, twisted and amplified by the rotating accretion disk and the spinning black hole itself. The exact mechanism that creates these jets is still not fully understood, but we know the basic outline. As matter spirals into the black hole, it drags magnetic field lines along with it. The rotation of the accretion disk and the spin of the black hole itself twist these field lines into a helical structure. Imagine taking a rubber band and twisting it over and over. Eventually, the tension builds up to the point where the rubber band wants to snap back. Something similar happens with the magnetic field lines near a black hole. The twisted magnetic fields become so tightly wound and energetically stressed that they act like a cosmic particle accelerator. Charged particles, mostly electrons and protons, get caught in these magnetic fields and are flung outward at tremendous speeds. The particles are accelerated to 99.9% of the speed of light or faster. They shoot out from the poles of the black hole, perpendicular to the plane of the accretion disk. Two jets emerge, one from each pole, creating a structure that looks like a cosmic hourglass with the black hole at the center. These jets can extend for millions of light-years, far beyond the galaxy that spawned them. To put this in perspective, our Milky Way galaxy is about 100,000 light-years in diameter. Some jets extend for 3 million light-years or more. That's 30 times the diameter of the Milky Way. The jets plow through the intergalactic medium, the thin soup of gas that exists between galaxies. As they propagate, they create shock waves that heat the surrounding gas and create enormous lobes of radio-emitting plasma. These lobes can be larger than galaxy clusters, spanning tens of millions of light-years. The energy required to create and sustain these jets is almost beyond comprehension. To accelerate matter to near light speed and keep it collimated in a narrow beam, just a few thousand light-years wide, across distances of millions of light-years, requires continuous power output equivalent to billions of suns. And this power output is sustained for millions of years. Over that time span, the total energy pumped into the jets can reach 10 to the 60 joules or more. That's about 100 billion times the energy of a supernova, spread out over millions of years instead of weeks. The jets aren't smooth beams of energy. They're turbulent, filled with instabilities and structures on multiple scales. High-resolution radio observations have revealed knots and filaments within the jets, regions where the plasma is compressed and energized, producing particularly bright emission. These knots sometimes appear to move faster than light, a phenomenon called superluminal motion. Of course, nothing actually moves faster than light. What we're seeing is a geometric effect. If a jet is pointed almost directly at us and moving at close to the speed of light, the light from different parts of the jet reaches us at almost the same time, creating the illusion that structures in the jet are moving across the sky faster than light. It's a relativistic trick of geometry, but it tells us just how close to light speed these jets are traveling. The jets interact with the surrounding intergalactic medium in complex ways. They can suppress star formation in nearby galaxies by heating the gas and preventing it from cooling and condensing. Or conversely, they can trigger star formation by compressing gas clouds as they plow through them. The total impact of these jets on their environment is enormous. They can reheat gas over regions spanning millions of light years, affecting the evolution of entire galaxy clusters. When one of these jets happens to be pointed directly at Earth, we observe what's called a blazar. Blazars are among the most variable objects in the sky. They can brighten or dim dramatically over periods of days or even hours, as instabilities in the jet cause fluctuations in the beam of radiation pointed toward us. Imagine standing in front of a cosmic searchlight that's flickering and pulsing as turbulence in the beam causes variations in the intensity. That's what we're observing when we see a blazar flare. The radiation from blazars spans the entire electromagnetic spectrum, from radio waves with wavelengths measured in meters to gamma rays with wavelengths smaller than atoms. And the gamma rays from blazars can be even more energetic than those from gamma ray bursts. Some blazar flares have been detected with individual photons carrying energies of several trillion electron volts. To understand how extraordinary this is, consider that visible light photons have energies of about 2 electron volts. A trillion electron volt photon has about 500 billion times more energy than a visible light photon. These ultra-high energy photons are created when electrons in the jet, already moving at 99.99% of the speed of light, collide with lower energy photons and boost them to extreme energies through a process called inverse Compton scattering. It's like a cosmic game of pool where an electron, moving at nearly light speed, strikes a photon and sends it flying off with a tremendous energy boost. The power channeled through these jets represents some of the most sustained energy output in the universe. Unlike gamma ray bursts, which are over in seconds, or supernovae, which fade in weeks, the jets from active galactic nuclei can persist for tens of millions of years. Over that time span, the total energy output can rival or exceed even the most powerful gamma ray bursts, and the jets leave their mark on the universe, carving out cavities in the intergalactic medium, heating gas over vast regions, and influencing the formation and evolution of galaxies across enormous volumes of space. The largest radio galaxies, powered by these jets, span more than 15 million light-years from end to end. To cross one of these structures at the speed of light would take 15 million years. They're some of the largest single structures in the universe, and they're all powered by a supermassive black hole at the center, converting the mass of stars into jets of near-light-speed particles. But jets and quasars aren't the only extreme objects in the cosmos. There's another class of objects that, while not necessarily outputting as much total energy, concentrate power in such an extreme way that they deserve consideration. Objects with magnetic fields so powerful they fundamentally alter the nature of matter itself. Magnetars. But we're not done yet. There's another class of objects that, while not necessarily outputting as much total energy, concentrate power in such an extreme way that they deserve consideration. Magnetars. Magnetars are a type of neutron star, the collapsed core left behind after a supernova. To understand what makes magnetars so extraordinary, we need to first understand neutron stars in general. Neutron stars are already among the most extreme objects in the universe. When a massive star goes supernova, the core collapses so dramatically that protons and electrons are squeezed together, forming neutrons. The result is a ball of almost pure neutrons, packed so tightly that it's essentially a giant atomic nucleus. They pack between 1.5 and 2 times the mass of our entire Sun into a sphere just 12 to 14 miles across. That's roughly the size of a city, containing more mass than our Sunday. The density is mind-boggling. A teaspoon of neutron star material, about 5 milliliters, would weigh approximately 4 billion tons on Earth. That's about the same mass as every car, truck, and bus on the planet combined, compressed into a volume you could hold in your hand. If you somehow brought that teaspoon of neutron star material to Earth, it would instantly fall through the ground, through the crust, through the mantle, and settle at the center of the Earth, because nothing on our planet is dense enough to support it. The gravity on the surface of a neutron star is approximately 200 billion times stronger than Earth's gravity. If you could somehow stand on a neutron star, you'd be flattened into a layer just a few atoms thick in a fraction of a second. But you wouldn't just be crushed. The intense gravity would also create enormous tidal forces. The difference in gravitational pull between your head and your feet, if you were standing upright, would be so extreme that you'd be stretched vertically and compressed horizontally simultaneously. This process, charmingly called spaghettification, would tear you apart at the molecular level before you even hit the surface. Neutron stars rotate incredibly fast. The fastest known neutron star, designated PSRJ 1748-2446 AD, rotates 716 times per second. That's more than 42,000 revolutions per minute. A point on its equator is moving at about 24% of the speed of light. At that rotation rate, the neutron star is almost at the limit of how fast it can spin without tearing itself apart from centrifugal force. Regular neutron stars have powerful magnetic fields, typically around 1 trillion Gauss, but magnetars take this to an entirely different level. Magnetars have magnetic fields up to 1,000 times stronger than those of regular neutron stars. And neutron stars already have the strongest magnetic fields of any known objects in the universe, except black holes, where the concept of a magnetic field becomes more complicated. A typical magnetar has a surface magnetic field strength of around 10 to the 14 to 10 to the 15 Gauss. That's 10,000 trillion to 100,000 trillion Gauss. For comparison, Earth's magnetic field is about half a Gauss. The magnetic field that protects us from solar radiation and cosmic rays, the field that makes compasses work, is about half a Gauss. A refrigerator magnet is about 100 Gauss. An MRI machine uses magnetic fields of about 10,000 to 30,000 Gauss. The strongest continuous magnetic field ever created in a laboratory is about 45 Tesla, which equals about 450,000 Gauss. That's the absolute limit of what we can achieve with our most advanced technology. A magnetar's field is 1 billion times stronger than that. At these field strengths, the very nature of matter changes. The quantum mechanical behavior of atoms and particles is dramatically altered by the presence of such an intense field. Atoms become elongated into thin, cigar-shaped spindles, hundreds of times longer than they are wide, aligned with the magnetic field. The way electrons orbit atomic nuclei changes. Chemical bonds work differently. The entire periodic table of elements would have different properties in a magnetar's magnetic field. Even the vacuum itself, the supposedly empty space, becomes polarized. According to quantum mechanics, the vacuum isn't truly empty. It's filled with virtual particles and antiparticles constantly popping into and out of existence. Normally, these virtual particles exist for such a short time that they have no observable effect, but in the intense magnetic field of a magnetar, the vacuum becomes birefringent, meaning light propagates differently depending on its polarization. The magnetic field literally changes the optical properties of empty space. If you could somehow bring a magnetar to within 1,000 miles of Earth, its magnetic field would be strong enough to erase every credit card, every hard drive, every magnetic storage device on the planet. All of our digital data would be gone in an instant. At a few hundred miles, the effects would become even more dramatic. The magnetic forces would be powerful enough to disrupt the chemical bonds in your body. Remember that chemical bonds are fundamentally electromagnetic in nature. They're created by the interaction of electrons between atoms. In a sufficiently strong magnetic field, these interactions are overwhelmed. Molecules start to fall apart. You wouldn't be crushed by gravity or fried by radiation first, though both would certainly kill you eventually. You'd be torn apart by magnetic forces acting on the iron in your blood, the electrons in your atoms, and the protons in your nuclei. Even the atomic nuclei themselves would begin to deform in the intense magnetic field. At field strengths above about 10 to the 16 Gauss, atomic nuclei become elongated, and the energy levels of nuclear states change. Magnetars occasionally produce bursts of energy called magnetar flares. These occur when the intense magnetic field causes the neutron star's crust to crack. To understand why this happens, imagine the crust of the neutron star as a solid shell about a kilometer thick. Despite the enormous gravity trying to crush everything down, the material is so dense that it forms a crystalline solid, somewhat like a metal but far denser and stronger. But the magnetic field is constantly evolving. As the magnetar rotates and the interior circulates, the magnetic field lines get twisted and tangled. This creates enormous stresses in the crust. Eventually, the stress becomes too great, and the crust cracks, similar to an earthquake on Earth but far more violent. When the crust shifts, even by just a few millimeters, magnetic field lines snap and reconnect, releasing enormous amounts of energy in a fraction of a second. It's similar to what happens in a solar flare, where magnetic field lines in the sun's atmosphere reconnect and release energy. But the magnetic fields in a magnetar are trillions of times stronger than those in the sun, so the energy release is proportionally greater. On the 27th of December 2004, a magnetar flare occurred in the constellation Sagittarius. The magnetar, designated SGR 1000, 806-20, is located about 50,000 light-years from Earth. In just 0.2 of a second, the flare released more energy than the Sun produces in 250,000 years. Let that sink in. In 1/5 of a second, less time than it takes to blink, this neutron star, 12 miles across, released 250,000 years worth of solar energy output. The burst of gamma rays and X-rays was so intense that it measurably affected Earth's ionosphere, the layer of charged particles in our upper atmosphere. Radio communications were temporarily disrupted. GPS signals were affected. Some satellites had to go into protective mode to avoid damage to their instruments. This was from an event that occurred 50,000 light-years away. The light and radiation had been traveling through space for 50,000 years, spreading out and weakening as it went, and it was still powerful enough to affect our planet in measurable ways. If a magnetar flare of that magnitude had occurred just 10 light-years from Earth, roughly the distance to the nearest stars, the radiation would have been 25 million times more intense. It would have been powerful enough to cause immediate and severe damage to the ozone layer. The ozone depletion would last for years. Ultraviolet radiation levels at the surface would skyrocket. Marine phytoplankton would die off. Terrestrial ecosystems would collapse. A mass extinction would likely follow. The most powerful magnetar flares can briefly outshine entire galaxies in gamma-ray and X-ray output. For a fraction of a second, a single neutron star 12 miles across can produce more high-energy radiation than hundreds of billions of stars. Magnetar flares are thought to be the source of at least some of the short-duration gamma-ray bursts we detect. The very short bursts, lasting less than 2 seconds, were originally thought to all come from neutron star mergers, but some of them have properties that don't quite match what we'd expect from mergers. They might be coming from magnetar giant flares, the most powerful type of magnetar flare. These are even more extreme than the 2004 event. The most powerful magnetar flare ever recorded occurred on the 5th of December, 1979, from a magnetar in the Large Magellanic Cloud, about 160,000 light-years away. The initial spike of gamma rays was so intense that it saturated detectors on multiple satellites, making it impossible to measure the peak energy accurately. It's estimated to have released about 10 to the 46 joules in a fraction of a second, comparable to a supernova, but released almost instantaneously instead of over weeks. What makes magnetars particularly fascinating from a physics perspective is that their power comes from neither fusion nor gravitational collapse, but purely from magnetic fields. The energy is stored in the twisted and tangled magnetic field lines threading through and around the neutron star. These field lines are under such enormous tension that they can fracture the neutron star's crust, and the crust itself is almost unimaginably strong. A single cubic centimeter of neutron star crust material has more tensile strength than a steel beam, 10,000 miles thick. The pressure required to deform this material is about 10 billion times greater than the pressure at the center of the Earth. Yet the magnetic field stresses are strong enough to crack it. This tells us something profound about the nature of the universe and the fundamental forces. We often think of gravity as the dominant force on cosmic scales. And it's true that gravity shapes the large-scale structure of the universe, holds galaxies together, and governs the motion of stars and planets. But electromagnetism, one of the 4 fundamental forces, is actually far stronger than gravity on a per-particle basis. The electromagnetic force between 2 electrons is about 10 to the 42 times stronger than the gravitational force between them. The only reason gravity dominates on large scales is that matter is usually electrically neutral, with equal amounts of positive and negative charge cancelling out. But in a magnetar, we see what happens when electromagnetic fields are allowed to reach their full potential. The magnetic field becomes so powerful that it rivals and even exceeds the gravitational binding energy of the neutron star. The fact that magnetars can exist at all, that they don't tear themselves apart immediately, is a testament to the incredible strength of neutron star matter. And the fact that magnetic fields can generate this kind of power enough to crack neutron star crusts and produce bursts visible across galaxies, tells us that electromagnetism is capable of concentrating energy in ways that rival gravity and nuclear forces. In the hierarchy of cosmic powerhouses, magnetars represent a unique category. They're not the most powerful in terms of total energy output. They're not the brightest in terms of sustained luminosity. But in terms of energy density, in terms of power concentrated in a small volume, in terms of the sheer extremity of the physical conditions, magnetars are unmatched. They're the universe's most powerful magnets, and they demonstrate that magnetic fields are not just minor players in the cosmic drama, but can be dominant forces capable of producing some of the most violent events in nature. Now, let's consider power from a different angle. Not the power of explosions or radiation, but the power to warp space-time itself. When 2 black holes spiral toward each other and merge, they create gravitational waves that ripple outward through the fabric of space-time at the speed of light. The first direct detection of gravitational waves occurred on the 14th of September 2015, when the twin detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, registered a distinctive chirp signal. The signal came from 2 black holes, 36 and 29 times the mass of the Sun, that had been orbiting each other for billions of years in a distant galaxy 1.3 billion light-years away. As they spiraled closer together, They accelerated, orbiting faster and faster, radiating energy in the form of gravitational waves. In the final fraction of a second before they merged, they were orbiting each other hundreds of times per second, with their event horizons separated by just a few hundred miles. The orbital velocity was approaching half the speed of light. Then they collided. In that final moment, as the two black holes merged into a single larger black hole, they released more power in gravitational waves than all the stars in the observable universe were producing in light at that moment combined. Let me repeat that, because it's almost impossible to believe. For a brief instant, the collision of these two black holes output more power than the combined light output of every star in the observable universe. The peak power output was approximately 3.6 times 10 to the 49 watts. That's 3.6 billion watts. To put this in perspective, the sun's luminosity is about 4 times 10 to the 26 watts. The merger was producing nearly 10 trillion times more power than the Sunday. All the stars in the observable universe together produce about 10 to the 49 watts. This single event, for a fraction of a second, exceeded that. But here's the crucial difference between this and the other powerful events we've discussed. Gamma-ray bursts release their energy as electromagnetic radiation, photons traveling through space. Supernovae and quasars do the same. Even magnetar flares release their energy as light and other forms of electromagnetic radiation. But gravitational waves are different. They're not electromagnetic. They're ripples in space-time itself, the very fabric of reality. When a gravitational wave passes through you, it doesn't hit you with particles or energy in the conventional sense. It temporarily changes the distance between points in space. As the wave passed through Earth in 2015, it stretched and squeezed space by about 1 part in 10 to the 21st. That means the entire Earth expanded and contracted by a distance far smaller than the diameter of a proton. The LIGO detectors are sensitive enough to measure changes in distance smaller than 1/10,000th the diameter of a proton across a 4-kilometer baseline. That's why it took decades of technological development to build detectors capable of observing gravitational waves. Since that first detection in 2015, dozens of gravitational wave events have been observed. Most are black hole mergers, but some are neutron-star mergers. The neutron-star merger, detected on the 17th of August 2017, was particularly significant because it was also observed with conventional telescopes. When two neutron stars merge, they produce not just gravitational waves, but also a burst of gamma rays, visible light, radio waves, and other electromagnetic radiation. This event, designated GW170817, allowed astronomers to study the same cosmic cataclysm with multiple types of instruments simultaneously. The observations confirmed that neutron star mergers are the source of short-duration gamma-ray bursts. They also confirmed that neutron star mergers are responsible for producing many of the heaviest elements in the universe, including gold and platinum. The merger ejected about 1/20th of a solar mass of heavy elements into space. That might not sound like much, but 1/20th of a solar mass is still about 6,000 Earth masses worth of gold, platinum, uranium, and other heavy elements. The collision itself released approximately 1% of the total mass of the two neutron stars as pure energy, in accordance with E equals mc squared. That's about 5 times 10 to the 46 joules, comparable to a powerful supernova, but released in just a few seconds rather than weeks. Black hole mergers are even more energetic in terms of gravitational wave output, but they're quieter in terms of electromagnetic radiation because black holes, by definition, don't emit light. When two black holes merge, there's no matter present to heat up and glow. The energy is released purely as gravitational waves. The most powerful black hole merger detected so far occurred on the 21st of May, 2019. designated GW190521. It involved two black holes of 85 and 66 solar masses, merging to form a final black hole of 142 solar masses. 9 solar masses, about 6,000 times the mass of Earth, was converted directly into gravitational wave energy in less than a tenth of a second. The peak power output reached approximately 5 times 10 to the 49 watts. These events represent power on a scale that's difficult to conceptualize. They're reshaping space-time itself across billions of light-years. So far, we've explored explosions, sustained radiation sources, magnetic field energy, and gravitational wave events. Each represents a different manifestation of power. But there's one more contender we need to consider, and it's perhaps the most fundamental of all, the event that started everything, the Big Bang itself. 13.8 billion years ago, the universe began. Not began in the sense of something happening somewhere in space, but began in the sense that space itself came into existence. Time itself came into existence. Before the Big Bang, there was no before, because time didn't exist. The very concept of before the Big Bang is meaningless. The universe began from what physicists call a singularity, a point of infinite density and infinite temperature where the laws of physics as we know them break down. In the first fraction of a second after the Big Bang, all the energy that would eventually become every galaxy, every star, every planet, and every particle in the observable universe was concentrated in a region far smaller than an atom. The temperatures in that first instant were so high that matter as we know it couldn't exist. Even atoms couldn't exist. Even atomic nuclei couldn't exist. Even protons and neutrons couldn't exist in their normal form. The universe was a seething soup of quarks and gluons, the fundamental constituents of matter, along with leptons like electrons and neutrinos, all in thermal equilibrium with an intense bath of radiation. The fundamental forces of nature, which we experience as distinct today, were unified into a single force. According to our best theories, at the very beginning, there was just one unified force governing all interactions. As the universe expanded and cooled, this symmetry broke down, and the forces separated one by one. First, gravity split off from the other forces at the Planck time, about 10 to the minus 43 seconds after the Big Bang. That's 0.0000, with 42 zeros, 0.1 seconds. That's the smallest meaningful unit of time in physics, determined by the speed of light, the gravitational constant, and Planck's constant. At times shorter than the Planck time, our current theories of physics don't apply. We don't know what happened during that first instant. String theory, loop quantum gravity, and other theories of quantum gravity attempt to describe this era, but we don't have experimental evidence to guide us. After gravity separated, the strong nuclear force split off at around 10 to the minus 36 seconds. Then the electromagnetic and weak nuclear forces separated at around 10 to the minus 12 seconds, when the universe was about a trillionth of a second old. By this point, the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, existed in the forms we know them today. But the universe was still incredibly hot and dense. The temperature was about 1,000 trillion degrees. At these temperatures, quarks and gluons couldn't bind together to form protons and neutrons. They existed as a free-flowing quark-gluon plasma. As the universe continued to expand and cool, it reached a critical temperature at about 1 microsecond after the Big Bang. At this point, quarks and gluons began to bind together to form protons and neutrons. This phase transition was one of the most important moments in cosmic history. If the strong nuclear force had been slightly different, stable protons might not have formed, and the universe would be radically different. By the time the universe was 1 second old, Its temperature had dropped to about 10 billion degrees. This was cool enough for some nuclear reactions to occur. Protons and neutrons began to fuse together, forming the first atomic nuclei. This era, called Big Bang nucleosynthesis, lasted for about 17 minutes. During this time, about 25% of the protons in the universe combined with neutrons to form helium nuclei. Small amounts of deuterium, the heavy form of hydrogen, and lithium were also created. But that was it. The universe was expanding and cooling too rapidly for heavier elements to form. For the next 380,000 years, the universe was opaque. It was filled with a hot plasma of atomic nuclei and free electrons. Photons of light couldn't travel far without being scattered by the free electrons. If you could somehow observe the universe during this time, it would look like being inside a glowing fog. You wouldn't be able to see any significant distance because the light would be constantly scattered. Then, when the universe was 380,000 years old, something crucial happened. The temperature had dropped to about 3,000 degrees, cool enough for electrons to bind to atomic nuclei, forming the first neutral atoms. This process is called recombination. Suddenly, the universe became transparent. Photons could travel freely through space without being scattered. The light from this era, stretched and redshifted by the expansion of the universe over the past 13.8 billion years, is what we detect today as the cosmic microwave background radiation. It's the afterglow of the Big Bang, a faint radio hiss coming from every direction in the sky. The cosmic microwave background has a temperature of just 2.7 degrees above absolute zero, but it contains an enormous amount of information about the early universe. Tiny variations in its temperature, about 1 part in 100,000, tell us about the density fluctuations that eventually grew into galaxies and galaxy clusters. After recombination, the universe entered what's called the Dark Ages. There were no stars yet, no galaxies, just neutral hydrogen and helium gas slowly collapsing under its own gravity into the denser regions. The first stars began to form about 100 to 200 million years after the Big Bang. These first stars were very different from stars today. They were massive, perhaps 100 to 300 times the mass of the Sun, and they burned hot and fast. They lived for just a few million years before exploding as supernovae, enriching the surrounding gas with the first heavy elements. The first galaxies formed as these early stars clustered together under the influence of dark matter, the invisible substance that provides extra gravitational pull. Over billions of years, galaxies merged and evolved into the structures we see today. Now, when we ask whether the Big Bang is the most powerful thing in the universe, we face a philosophical question. The amount of energy involved in the Big Bang wasn't just larger than any explosion we've discussed. It was all the energy that exists in the universe. Every photon of light from every star, every ounce of matter in every galaxy, which is itself frozen energy, according to E equals mc squared, every gravitational wave, every magnetic field, every electron, proton, and neutron. All of it came from the Big Bang. The total energy in the observable universe, including matter, dark energy, and radiation, is approximately 10 to the 70 joules, maybe more, depending on what lies beyond the observable horizon. In terms of total energy, nothing can compare to the Big Bang because the Big Bang is the origin of all energy in the universe. But there's a question about whether we can meaningfully call the Big Bang the most powerful thing in the universe. Is it a thing in the universe, or is it the event that created the universe? It's not a phenomenon that occurs within space-time. It's the origin of space-time itself. And there's a practical consideration. The Big Bang, as a singular event, is over. It happened once, 13.8 billion years ago. We can't observe it directly. We can only observe its after effects. the cosmic microwave background radiation, the expansion of the universe, and the abundances of light elements. In that sense, while the Big Bang is certainly the most energetic event in cosmic history, the ultimate beginning, it might not satisfy our search for the most powerful thing currently existing or occurring in the universe. For that, we need to look at something that's still active today, something that's been working since the Big Bang and continues to grow stronger, something that most people have never even heard of. That brings us to our final contender, dark energy, the most powerful force in the universe. And the story of its discovery is one of the most remarkable in the history of astronomy. In 1998, two independent teams of astronomers made a discovery that would fundamentally change our understanding of the universe. The Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were studying distant supernovae. Specifically, they were looking at type Ia supernovae, a particular kind of supernova that always releases approximately the same amount of energy. Type Ia supernovae occur when a white dwarf star in a binary system accumulates too much mass from its companion star. When the white dwarf reaches about 1.4 times the mass of the Sun, called the Chandrasekhar limit, it can no longer support itself against gravity. The white dwarf collapses and explodes in a thermonuclear runaway that completely destroys the star. Because this process always happens at the same mass threshold, type Ia supernovae always release approximately the same amount of energy, making them excellent standard candles. A standard candle is an object whose intrinsic brightness is known. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it is. The farther away an object is, the dimmer it appears. Following the inverse square law, by measuring type Ia supernovae in distant galaxies, astronomers could determine how far away those galaxies are with unprecedented accuracy. But the real goal wasn't just to measure distances, it was to measure the expansion rate of the universe and how it's changing over time. According to standard cosmology, the universe has been expanding since the Big Bang. Galaxies are moving away from each other, carried along by the expansion of space itself, but gravity should be slowing this expansion down. Every galaxy pulls on every other galaxy gravitationally, and this should be acting like a brake, gradually decelerating the expansion. The question was, how strong is this deceleration? Is it strong enough that the universe will eventually stop expanding and begin to contract in a big crunch? Or is it weak enough that the universe will expand forever, gradually slowing but never stopping? By measuring supernovae at different distances, corresponding to different times in the past, due to the time it takes light to travel, astronomers could determine how the expansion rate has changed over cosmic history. Both teams expected to find that the expansion was decelerating. The only question was by how much. But that's not what they found. Instead, they discovered that the expansion of the universe is accelerating. Distant supernovae were dimmer than expected, which meant they were farther away than they should be if the expansion was decelerating. Galaxies aren't just moving away from each other. They're moving away faster and faster as time goes on. Something is pushing the universe apart, counteracting gravity on the largest scales. The discovery was so unexpected that both teams initially thought they'd made a mistake. They checked their data, recalibrated their instruments, looked for possible sources of error. Maybe dust was dimming the supernovae, making them appear farther away than they really were. Maybe there was some unknown systematic error in the measurements. But no matter how they analyzed the data, the conclusion was the same. The expansion of the universe is accelerating. In 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics for this discovery. The force driving this acceleration was named dark energy, in analogy with dark matter. Just as dark matter is invisible matter that we detect through its gravitational effects, dark energy is invisible energy that we detect through its effect on the expansion of the universe. But dark energy is far more mysterious and far more powerful than dark matter. We don't know what dark energy is. We don't know why it exists. We don't even know if it's truly a form of energy or if it's something else entirely, perhaps a property of space itself. But we know it's real, and we know it's powerful. Dark energy makes up approximately 68% of the total energy content of the universe. Dark matter, the invisible substance that provides the extra gravity holding galaxies together, makes up about 27%. Ordinary matter, everything made of atoms, all the stars and planets and gas and dust and people, makes up just 5% of the universe. Think about that for a moment. Everything we can see, everything we've ever observed with telescopes, every star and galaxy and nebula, every planet and asteroid, every person who has ever lived, all of it combined, makes up just 5% of the universe. We are a tiny minority component in a universe dominated by things we don't fully understand. Dark energy behaves unlike anything else in physics. To understand why it's so strange, we need to think about how different forms of energy behave as the universe expands. As the universe expands, ordinary matter becomes more diluted. If you have a certain number of atoms in a given volume of space, and you double the volume, you now have half as many atoms per unit volume. The density of matter decreases as the universe expands. Radiation, including light, also becomes diluted, but it experiences an additional effect. As space expands, the wavelengths of photons are stretched. This is called cosmological redshift. A photon that was emitted as blue light from a distant galaxy billions of years ago might arrive at Earth as infrared radiation because its wavelength has been stretched by the process. Expansion of space. Longer wavelength means lower energy, so each individual photon loses energy as the universe expands. Combined with the dilution effect, radiation density decreases even faster than matter density as the universe expands. But dark energy is different. Dark energy doesn't dilute as space expands. Its density remains constant even as the volume of the universe increases. If you double the volume of space, the energy density of dark energy stays the same. That means as the universe grows, the total amount of dark energy increases. It's as if empty space itself has energy, and when you create more space through expansion, you create more dark energy. This property is completely unprecedented in physics. Nothing else behaves this way. It's so strange that many physicists initially refused to believe the supernova results, but subsequent observations have confirmed it beyond doubt. Measurements of the cosmic microwave background by satellites like WMAP and Planck have independently confirmed the existence of dark energy. Observations of large-scale structure, the way galaxies are distributed across the universe, also point to dark energy. Measurements of baryon acoustic oscillations, patterns in the distribution of galaxies that arose from sound waves in the early universe, provide yet another confirmation. All the evidence points to the same conclusion. Dark energy is real. It makes up about 68% of the universe, and it's causing the expansion of the universe to accelerate. This property leads to a remarkable conclusion about power. Dark energy is the ultimate source of power in the universe. Every second, dark energy is accelerating the expansion of space, pulling galaxies apart against the force of gravity. The amount of energy required to do this is staggering. Let's put this in perspective by comparing dark energy to all the other forms of energy in the universe. All the stars in the observable universe together have a combined mass of about 10 to the 53 kilograms. That's a 1 followed by 53 zeros. Using E equals mc squared, if you could convert all that stellar mass to pure energy, you'd get about 9 times 10 to the 69 joules. That's every star in the observable universe, hundreds of billions of trillions of stars, completely annihilated and converted to energy. The dark energy in the observable universe contains approximately 10 to the 70 joules of energy. It's not just more energy than all the stars. It's more energy than all the ordinary matter, all the dark matter, all the radiation, everything else combined. And this energy is continuously driving the expansion of the universe. The power output, in terms of the rate at which dark energy does work against gravity to expand space, is beyond any meaningful comparison with the other phenomena we've discussed. A supernova releases about 10 to the 46 joules over a few weeks. A gamma-ray burst releases about 10 to the 51 joules over a few seconds. A black hole merger releases about 10 to the 48 joules of gravitational wave energy in a fraction of a second. Dark energy operates on an entirely different scale. It's not localized to a single event or a single region of space. It operates everywhere, across billions of light years, continuously, without pause, without end. Every cubic meter of space contains dark energy. The energy density is tiny, about 5 times 10 to the minus 10 joules per cubic meter. That's about the energy equivalent of 3 hydrogen atoms per cubic meter. But when you multiply that tiny density by the enormous volume of the observable universe, roughly 4 times 10 to the 80 cubic meters, you get an absolutely staggering total. And remember, the observable universe is just the region of space from which light has had time to reach us. The entire universe is almost certainly much larger, perhaps infinitely large. If the universe is infinite, then the total amount of dark energy is infinite. But even just considering the observable universe, dark energy dominates everything else. Recent observations from the Dark Energy Spectroscopic Instrument, DESI, have suggested something even more intriguing. Dark energy might not be constant. It might be changing over time. DESI has been measuring the expansion history of the universe with unprecedented precision by observing millions of galaxies and quasars. Preliminary results suggest that the density of dark energy might have been slightly different in the past. If confirmed, this would mean dark energy is not the cosmological constant that Einstein proposed, but something more dynamic, something that evolves, something that might be growing stronger, or possibly weaker. If dark energy is strengthening over time, the implications are profound and unsettling. Every second, dark energy is accelerating the expansion of space, pulling galaxies apart against the force of gravity. The amount of energy required to do this is staggering. Let's put this in perspective. All the stars in the observable universe together have a combined mass of about 10 to the 53 kilograms. Using E equals mc squared, if you could convert all that matter to pure energy, you'd get about 9 times 10 to the 69 joules. That's every star in the observable universe, completely annihilated. The dark energy in the observable universe contains approximately 10 to the 70 joules of energy. It's not just more energy than all the stars. It's more energy than all the matter, all the dark matter, all the radiation, everything else combined. And this energy is continuously driving the expansion of the universe. The power output, in terms of the rate at which dark energy does work against gravity to expand space, is beyond any meaningful comparison. It operates on cosmic scales, across billions of light years, continuously, without pause, without end. Recent observations from the Dark Energy Spectroscopic Instrument have suggested that dark energy might not be constant. It might be changing over time, possibly growing stronger or weaker. If this is confirmed, it could mean that dark energy is even more dynamic and powerful than we thought. Some theoretical models suggest that if dark energy continues to strengthen, it could eventually become powerful enough to tear apart not just galaxy clusters, but individual galaxies, solar systems, planets, and ultimately atoms themselves. This hypothetical scenario is called the Big Rip, and it represents the ultimate triumph of dark energy over all other forces in nature. Let me walk you through what would happen in a Big Rip scenario. Currently, dark energy is powerful enough to accelerate the expansion of the universe on the very largest scales. It's pulling galaxy clusters apart, but it doesn't affect individual galaxies or solar systems because on those smaller scales, gravity is still strong enough to hold things together. Our local group of galaxies, which includes the Milky Way, Andromeda, and about 50 smaller galaxies, is gravitationally bound. Dark energy isn't strong enough to tear it apart. Similarly, dark energy doesn't affect the orbits of planets around stars or the orbits of electrons around atomic nuclei. Gravity, electromagnetism, and the nuclear forces are all much stronger than dark energy on these scales. But if dark energy is growing stronger, as some interpretations of recent data suggest, then eventually it will become powerful enough to overcome these forces. The timeline for a Big Rip depends on how quickly dark energy strengthens. In some models, it happens in 20 billion years. In others, it might take 50 billion years or more. Let's assume a timeline of about 50 billion years from now, which is one of the more commonly cited estimates. Here's how it would unfold. For the first few billion years, nothing seems dramatically different. The universe continues expanding, galaxies continue drifting apart, stars continue their normal life cycles. But the rate of acceleration gradually increases. About 20 billion years from now, galaxy clusters begin to be torn apart. The Virgo cluster, the nearest large cluster of galaxies, containing thousands of galaxies, starts to disperse. The galaxies that were gravitationally bound to the cluster are pulled away by the strengthening expansion. About 1 billion years before the end, individual galaxies begin to be shredded. The gravitational binding energy of a galaxy, the energy required to completely disperse all its stars into intergalactic space, is enormous. For the Milky Way, it's about 10 to the 53 joules. But dark energy, by this point, has grown strong enough to provide that much energy over the volume of the galaxy. Stars are ripped away from the galactic disk and flung into the void. The Milky Way, which has existed in recognizable form for more than 10 billion years, is torn apart. About 3 months before the end, solar systems begin to be destroyed. Earth's orbit around the Sun, which has been stable for 4.5 billion years, is disrupted. The gravitational binding energy of the solar system, the energy holding the planets in orbit, is overcome by the expanding space between the Sun and the planets. Earth drifts away from the Sun, along with all the other planets. At this point, any hypothetical observers would notice something terrifying. The Sun would appear to be shrinking rapidly in the sky, not because the Sun itself is changing, but because the distance between Earth and the Sun is increasing exponentially. Within weeks, the Sun would fade to a dim point of light. About 30 minutes before the end, planets and stars themselves begin to be torn apart. The gravitational binding energy of Earth, the energy holding our planet together against its own self-gravity, is about 2 times 10 to the 32 joules. Dark energy, now impossibly strong, overwhelms this. The surface of the Earth begins to bulge outward. Tectonic stress exceeds anything the planet has ever experienced. Massive earthquakes shake the entire globe. The atmosphere begins to escape into space, not gradually as it would from normal processes, but explosively. Within minutes, Earth is shredded into fragments, each fragment itself continuing to be pulled apart. Stars undergo the same fate. The Sun, held together by its own gravity for 5 billion years, is torn apart. The nuclear fusion in its core ceases as the core is disrupted. The star explodes, but not in a supernova, in a different kind of explosion driven by external forces rather than internal pressure. With just a fraction of a second remaining, molecules and atoms are torn apart. The electromagnetic force binding electrons to atomic nuclei, one of the strongest forces in nature, is overwhelmed by dark energy. Atoms are ionized, their electrons ripped away, but it doesn't stop there. In the final tiny fraction of a second, atomic nuclei themselves are torn apart. The strong nuclear force, the force that binds protons and neutrons together in atomic nuclei, is one of the most powerful forces in the universe. It's what holds atoms together against the electromagnetic repulsion of protons. It's what powers nuclear weapons and nuclear reactors. But even the strong nuclear force is overwhelmed. Protons and neutrons are ripped apart into their constituent quarks. The universe, at this point, has been reduced to a sea of elementary particles, all being pulled apart by space expanding faster than the speed of light. And then, the universe reaches a singularity. All of space has been torn apart. Even space-time itself breaks down. The Big Rip is, in some ways, the opposite of the Big Bang. The Big Bang was a singularity at the beginning, where everything came from a single point. The Big Rip would be a singularity at the end, where everything is torn apart into disconnected points. Now, it's crucial to emphasize that the Big Rip is a theoretical scenario. We don't know if dark energy is actually strengthening. The DESI observations that hint at changing dark energy are preliminary and need to be confirmed by further observations. Even if dark energy is changing, it might be weakening rather than strengthening, or it might oscillate, or it might asymptotically approach some constant value. There are other possible fates for the universe. If dark energy remains constant, as most current models assume, the universe will continue expanding forever, but won't experience a big rip. Instead, it will undergo what's called heat death, or the big freeze. Stars will eventually exhaust their fuel. New stars will stop forming as galaxies run out of gas. The universe will become darker and colder as existing stars die. White dwarfs will cool to become black dwarfs. Neutron stars will slowly radiate away their heat. Even black holes will eventually evaporate through Hawking radiation, a quantum mechanical process predicted by Stephen Hawking. The evaporation time for a black hole depends on its mass. Small black holes evaporate faster. A black hole with the mass of the Sun would take about 10 to the 67 years to evaporate. That's a 1, followed by 67 zeros, far longer than the current age of the universe. Supermassive black holes would take even longer. A black hole with 1 billion solar masses would take about 10 to the 98 years to evaporate. But eventually, given enough time, even these will vanish. In the extreme far future, perhaps 10 to the 100 years from now or more, the universe would be a vast, cold, dark expanse. No stars, no galaxies, no planets, just isolated particles, widely separated, drifting through an ever-expanding space. The temperature would asymptotically approach absolute zero. Entropy would reach its maximum. Nothing would happen anymore because there would be no energy gradients to drive any processes. This is the heat death of the universe, and it's the most likely fate according to our current understanding. It's not as dramatic as the Big Rip, but in its own way, it's just as absolute an ending. A third possibility is the Big Crunch. If dark energy were to weaken or disappear, and if there's enough matter in the universe, gravity could eventually overcome the expansion. The universe would stop expanding and begin to contract. Galaxies would start moving toward each other instead of away. Over billions of years, the universe would collapse back in on itself, getting denser and hotter as it contracts. Eventually, all matter would be crushed together in a singularity similar to the Big Bang, but in reverse. However, based on current observations, there doesn't seem to be enough matter to cause a big crunch, and dark energy shows no signs of weakening. So the Big Crunch is considered the least likely of the three scenarios. What we do know for certain is that dark energy is real, it's powerful, and it's in control of the universe's ultimate fate. Whichever ending the universe eventually faces, whether it's the heat death, the Big Rip, or something else we haven't thought of, dark energy will play the dominant role in determining that fate. It's the most powerful force in the cosmos, operating on the largest scales, determining the destiny of everything that exists. And perhaps the most humbling aspect of all this is that we still don't really understand what dark energy is. We've given it a name, we've measured its effects, we've calculated its energy density. But the fundamental nature of dark energy remains one of the biggest unsolved problems in physics. Is it a cosmological constant, a property of space itself that never changes? Is it a dynamic field, like the Higgs field, that can vary in strength? Is it something to do with quantum mechanics, related to the energy of the vacuum, or is it something completely different, something that will require new physics to understand? The discovery of dark energy has revolutionized cosmology, but it's also revealed just how much we still don't know about the universe we live in. And that's one of the most exciting aspects of modern astronomy. We're living in an era where we're making fundamental discoveries about the nature of reality itself. The universe is stranger and more wonderful than anyone imagined just a few decades ago. So, after our journey through the cosmos, from exploding stars to colliding black holes, from magnetars to quasars, what's the answer? What is the most powerful thing in the universe? The answer, as we've discovered, depends on how you define power. If we're measuring power by instantaneous output, by sheer concentrated fury released in a single moment, then black hole mergers win, hands down. For a fraction of a second, two black holes spiraling together and merging can output more power than every star in the observable universe combined. 3 solar masses converted directly into gravitational wave energy, shaking the fabric of space-time across billions of light-years. It's power on a scale that briefly exceeds everything else happening in the universe at that moment. If we're measuring power by sustained luminosity, by the ability to shine brilliantly across the universe for millions of years, then quasars and active galactic nuclei are the undisputed champions. A single quasar can outshine 500 galaxies like the Milky Way, maintaining this extraordinary output for millions of years as matter spirals into a supermassive black hole. The jets from active galactic nuclei extend for millions of light-years, carving cavities in the intergalactic medium and influencing the evolution of galaxy clusters. If we're measuring power by energy density and magnetic field strength, by the ability to fundamentally alter the nature of matter and even change the properties of the vacuum itself, then magnetars take the crown. With magnetic fields 1 billion times stronger than anything we can create on Earth. Magnetars demonstrate that electromagnetism can concentrate power in ways that rival the other fundamental forces. They can crack their own neutron star crusts, which are stronger than steel beams, thousands of miles thick, and produce flares that affect planets thousands of light-years away. If we're measuring power by explosive force and the creation of new elements, by the ability to forge the heavy atoms that make planets and life possible, then hypernovae and gamma-ray bursts are unmatched. These cosmic detonations release more energy in seconds than our Sun will produce in its entire 10 billion-year lifetime, creating elements that can't be forged in any other way, and potentially causing mass extinctions across interstellar distances. Each of these phenomena represents a different aspect of cosmic power. Each one pushes the laws of physics to their extreme limits. Each one demonstrates that the universe operates on scales of energy and violence that dwarf anything in human experience. But if we're measuring power by total energy, by the ability to control the destiny of the entire universe, by the sheer scope of influence, across billions of light years and billions of years of time, by the capacity to determine the ultimate fate of everything that exists, then there's only one answer: dark energy. And it wins not by a narrow margin, but by an overwhelming majority. Dark energy contains more energy than everything else in the universe combined, more than all the ordinary matter, all the dark matter, all the radiation, all the kinetic energy of motion, everything. It represents 68% of the total energy budget of the universe. It's not flashy like a gamma-ray burst. It doesn't announce itself with brilliant light like a quasar. It doesn't create spectacular explosions like a hypernova. It doesn't send out gravitational waves like merging black holes. It works slowly, invisibly, inexorably, but it commands the fate of absolutely everything that exists. Think about the implications of that for a moment. Every galaxy you can see through a telescope, every star that lights up the night sky, every planet orbiting every one of those stars, every atom in every one of those planets, all of it is subject to the influence of dark energy. There is no escape from it. You can shield yourself from radiation with lead. You can escape a gravitational field by traveling fast enough. You can avoid being torn apart by a magnetar by simply being far away from one. But you cannot escape dark energy. It's woven into the fabric of space itself. Everywhere there is space, there is dark energy. And space is expanding, driven by that energy, pulling everything apart. It has more energy than all the matter in the universe combined. It's accelerating the expansion of space itself, pulling the cosmos apart at an ever-increasing rate. And here's what makes it even more remarkable. It's been doing this since the universe was about 4 billion years old. For the first 4 billion years after the Big Bang, the expansion of the universe was decelerating. As expected, gravity was winning, slowing the expansion. But then, when the universe had expanded enough that matter became sufficiently diluted, dark energy began to dominate. And since then, for the past 9 billion years, dark energy has been in control. The universe has been accelerating, expanding faster and faster, and it's not going to stop. In the end, dark energy will win. Not just win, but win absolutely and completely. Long after the last stars have burned out, perhaps 100 trillion years from now, when the last red dwarf stars exhaust their fuel, the universe will still be expanding. Long after the last black holes have evaporated through Hawking radiation, perhaps 10 to the 100 years from now, an almost incomprehensible span of time, the universe will still be expanding. The galaxies will have drifted so far apart that their light can no longer reach each other. Any hypothetical observers in one galaxy wouldn't be able to see any other galaxies. They would see only their own galaxy, surrounded by absolute darkness in all directions. Eventually, even their own galaxy would evaporate, stars drifting apart into the void. The universe will become a cold, dark, essentially empty expanse of space, with isolated particles separated by billions of light years, all moving away from each other as space continues to expand. The temperature will approach absolute zero. No stars will shine. No processes will occur. Nothing will happen anymore because there will be no energy gradients to drive any events. This is the heat death of the universe, and dark energy is the force that makes it inevitable. That is true power. Not the power to destroy in an instant. Though if the Big Rip scenario is correct, dark energy can do that too, tearing apart galaxies, stars, planets, and even atoms when it grows strong enough. But the power to shape the structure of reality itself, the power to determine the ultimate fate of everything that exists, the power to do so on a time scale that makes the lifetime of stars seem like the blink of an eye and the age of galaxies seem like a fleeting moment. Consider the cosmic timeline. The universe is currently 13.8 billion years old. Dark energy has been dominant for about 9 billion years of that time, roughly 2/3 of cosmic history. But the era of stars, the era we're living in now, where stars shine and galaxies are visible, and the universe is full of light and activity, will last perhaps another 100 trillion years. That sounds like an incredibly long time, and by human standards it is. But compared to the ultimate future of the universe, it's nothing. After the last stars die, the universe will continue existing in darkness for an almost infinitely longer time. If the universe lasts forever, as seems likely, then the era of stars represents just the first tiny fraction of cosmic history, an infinitesimally small beginning. The vast majority of the universe's existence will be spent in a dark, cold, expanding state, driven by dark energy. We happen to be living in a very special time. We're alive during the era when stars shine, when galaxies are visible, when the universe is young and active and full of interesting events. In the far future, that won't be the case anymore. And dark energy is the reason why. We live in a universe where exploding stars can forge atoms, where black holes can merge and shake the fabric of space-time, where magnetic fields can become strong enough to alter the quantum vacuum, where quasars can shine with the brilliance of trillions of suns. These are all extraordinary phenomena that demonstrate the extreme conditions and energies that exist in our universe. But all of these phenomena, as remarkable as they are local events. They happen in specific places at specific times. A supernova occurs in one star, in one galaxy. A gamma-ray burst shoots out from one hypernova. A quasar shines from the center of one galaxy. A magnetar flare erupts from one neutron star. A black hole merger happens when two specific black holes collide. They're isolated events, however powerful they might be. Dark energy is different. It's not localized. It's not isolated. It's everywhere, at all times, affecting everything. It's operating right now, in the space between the galaxies, in the space between the stars, in the space between the atoms, in the space between the quarks inside atomic nuclei. Everywhere there is space, dark energy is there, driving the expansion. It's the dominant force in the cosmos, and it's accelerating toward an endgame we're only beginning to understand. The most powerful thing in the universe isn't a thing at all in the conventional sense. It's not an object, not a star, or a black hole, or a galaxy. It's a property of space itself, a mysterious energy that permeates the vacuum, and it's pulling the universe apart with a force that nothing can resist. In our search for cosmic power, we've discovered supernovae that forge the elements of the periodic table and distribute them across space, making planets and life possible. We've found gamma-ray bursts that can sterilize entire regions of a galaxy, representing potential existential threats across interstellar distances. We've observed quasars that outshine trillions of stars, demonstrating the power of supermassive black holes devouring matter. We've detected magnetars with fields that fundamentally change the nature of matter and space. We've measured gravitational waves from black holes colliding with a peak power output that exceeds every star in the visible universe. Each discovery has been extraordinary. Each one has pushed our understanding of physics and the universe to new limits. But in the end, the most powerful force is the one we understand the least. The one that was discovered just 26 years ago. The one that's been there since the universe was 4 billion years old, quietly working in the background, growing ever stronger as the universe expands. The one that's shaping the cosmos on the grandest scale imaginable. Dark energy is the universe's ultimate power. It has been determining the fate of the universe for the past 9 billion years, and it will continue to do so for all eternity. While supernovae and gamma-ray bursts are transient events that last for seconds or weeks, while quasars shine for millions of years before fading, while even black holes will eventually evaporate, given enough time. Dark energy is eternal. It doesn't fade. It doesn't run out of fuel. It doesn't weaken over time. If anything, it might be growing stronger. It's the ultimate power in the universe, operating on the ultimate scale, determining the ultimate fate of everything. And it's just getting started. The universe is only 13.8 billion years old. Dark energy has been dominant for only 9 billion years. Ahead lies an eternity of expansion, an infinite future where dark energy continues to accelerate the growth of space, pushing the contents of the universe farther and farther apart, until eventually, every particle is separated from every other particle by distances so vast that they might as well be in separate universes. That is the power we were searching for. Not power that destroys in an instant, but power that shapes eternity. Not power that operates on human timescales or even stellar timescales, but power that operates on cosmic timescales and determines the ultimate destiny of everything. The answer to our question, what is the most powerful thing in the universe, is dark energy. And perhaps what's most remarkable is that we live in the era when we discovered it. We're among the first generations of humans to know that dark energy exists, to understand that the universe is accelerating, to realize that the cosmos we see around us is just a tiny fraction of cosmic history. Tens of billions of years from now, if any intelligent beings exist, they won't be able to discover dark energy the way we did. The galaxies will be so far apart that they won't see the expansion. They'll look out into the sky and see only their own galaxy, surrounded by darkness. They won't know that the universe is bigger than what they can see. They won't know that the universe is expanding. They won't discover dark energy. We're living in a privileged time in cosmic history, when the universe is just old enough that dark energy has become dominant, but just young enough that we can still see other galaxies and measure the expansion. A cosmic window that's open now but will eventually close. And through that window, we've discovered that the universe is even stranger and more wondrous than we ever imagined. Tonight, you've journeyed through the most extreme phenomena the cosmos has to offer. You've witnessed the fury of dying stars and the birth of black holes. You've seen magnetic fields strong enough to tear matter apart and gravitational waves that shake the universe. You've explored quasars that outshine trillions of stars and gamma-ray bursts that release more energy in seconds than our sun will produce in its entire life. And you've learned that the most powerful force of all is one that most people have never even heard of, one that we're only beginning to understand. Dark energy, the mysterious force that makes up more than 2/3 of the universe, is accelerating the expansion of space itself, determining the fate of everything that exists, operating on a scale that dwarfs every other phenomenon we've discussed tonight. It's the ultimate cosmic power, and it's the answer to our question. The universe is far stranger, far more powerful, and far more wonderful than we ever imagined, and we're only just beginning to understand the forces that govern it. If you found this journey through cosmic power fascinating, make sure you're subscribed so you don't miss future explorations of the universe's greatest mysteries. The cosmos is full of wonders waiting to be discovered, and we're just getting started. Thanks for watching, and until next time, keep looking up.